Hello everyone. So this is a session on natural language processing, and one of the aspect of a natural language processing area that is uh, uh, basically we'll discuss about the graph neural network. Though graph neural networks are very general in terms of the problems that we solve using GNNs, so it can be image or video or knowledge graphs or any textual data. So it is not specific to or constrained with only textual problems, but we can actually solve a variety of problems using graph neural networks. And in recent times, graph neural network has become very popular, and there are several research and work has been done on this area. So it's very important that we understand the advantages and the powerful network like GNN, and the variations of GNN, so we can actually implement it to probably in future advancement of the existing networks that we have currently. Okay, so with that note, let me go ahead with the slides. So I will be talking about introduction to GNN and the prerequisites. I'll have an idea of, I'll go ahead with the tasks and how the GNNs are formed, and we'll go little in depth of GNNs, and we'll have a code walkthrough quick on that. And so with that note, let's understand what graph neural networks are. Okay, so graph neural networks are a class of neural network models suitable for processing graph structured data, right? So we can have different structures of data. So as we know already, we can have semi-structured, right? A structured or probably a non-structured data. So based on that, we actually decide what what kind of algorithm that we need to use on those scenarios. Okay, all right. So in many real world applications, including let's say social media and information exchange or chemical biological domains, we have a lot of use cases using GNN that we actually can solve. So these places where the data is very scattered and not uh, like organized, we actually look for model graphs or a graph neural network um, implementation. So what are graph neural networks? If you see in the image, right, it's a convolutional network with a graph convolutional. So there, these two are not much different. I mean, in terms of how they are linked, but probably at by looking at them and how they are uh, uh, distributed, that is different. So, what is the main difference between a CNN and a graph neural network? So the answer would be the only the input data that changes with the graph neural network, right? So in CNN, whatever we can imagine the input, right, as a vector, and the output that we get, GNN also works in similar fashion. Only the input data that is more of a unstructured or semi-structured data that we pass into the network, or it could be a structured data as well. So in NLP, as this session is specific to natural language processing, in NLP we have graphs almost everywhere. So if you see, there are dependency parsing trees where we actually use dependency graphs, where again we use different connected nodes where these nodes are directed to each other and having a multiple directed graphs for these nodes. So let's say here a root node with Saw and John and Mary, right? I mean, just for as an example, it has been taken, so you can understand that they are kind of directed graph. So there are in dependency parsing, we have a lot of problems that are coming in NLP and which can be better. I mean, which we can solve in a better way using GNNs. Okay, so GNN plays a great role in that aspect. Okay, so there is a question. Could you please explain the difference between CNN and graphs? So there is, if you think about irregular and regular data structures, right? So let's say regular data structure where we have metrics, and we in CNN, if you we do I mean, I will just cover an overview of an upper layer, because I expect the CNN and an idea of CNN should be there before we understand the GN or GCN. So normally in CNN we have a pooling layer, right? And you have a matrix where you pull a certain based on the kernel that you have, right? So you pull a certain matrix or adjacency matrix from the convolutional layer, right? So in GNN also we do the same thing. I will come to GNN how that is formulated, so you'll have a better idea. But for just to have an idea of CNN, so that's what we do in CNN, that we pull a layer from the given matrix, let's say. So there is another question: is GNN is used only in NLP, and is there a use case in vision and other places? As I have mentioned at the beginning of this session, yes, NLP is one of the aspects that GNN is used for. I mean, GNN can be used for textual, image, video, or knowledge processing. I mean, as you if you you might have heard about knowledge graphs recently, so which are actually being solved by GNNs. And GNNs can be used for generating graphs. So you wanted to generate some graphs based on your data set, you can use GNN. So GNNs can be used for classification, POS, NER tagging, I mean, in terms of NLP problems, let's say. And in convolutional layers, I mean, in image segment, image recognition, we can use GNN. Okay, so there are a lot of applications that are formulated using GNN, though I will not be covering the aspects of image or video processing here using GNN, as this is more of a focused on NLP side. But yes, that this can be used for any of these areas. Okay, so there are dependency graphs that are, this is an example from Allen NLP. So they have a very nice example of dependency graphs and how each of the words are linked with other words, right? The verb and or preposition and prepositional phrases are linked to each other. So those are actually formulated using dependency graphs. There are social media connections. Those are also kind of an example of having a I mean, having a graph, network or graph data structure being used there. And this is kind of a knowledge graph where you actually derive the names for a particular organization or business terms from a particular domain, right? So these also kind of link to each other as a knowledge graph uh, structure. So there's another question. Can GNN be used to add, modify, delete any graph nodes in knowledge graphs? Usually, this is the most laborious task of using knowledge graph based models. So, as I said, GNN can be used for generating new graphs, and there are a lot of research that's going on still on this area that where we actually find knowledge graphs doesn't produce each of the nodes properly, or sometimes they are tend to give very high accuracy in terms of overfitting. So those problems are kind of nowadays being solved using GNNs. Now, which variety of GNN we should be using, that's a very uh, uh, business use case kind of a question. So what you are going to implement, based on that you would be choosing the GNN type. So GNN is just a, you can say, vanilla RNN. So like that, I have just taken GNN, but there are uh, so many variations of graph neural network. Okay, so I'll go ahead. So why GNN for NLP? So if you see the left side, right? So here the accuracy of uh, and in the data set fraction graph. So here it shows the LSTM has 70% data set, and with a 100% data set, and with a knowledge graph LSTM within 70% data set, which is doing better here, right? So that's kind of an indication that with the news 20 data set, it's going better in that direction of having less data set and getting high accuracy. So that is kind of a good sign that we should be using GNN. And another thing is from this paper where they have a comparison with knowledge graph LSTM and LSTM, and the accuracy and data fraction is an SNLI data set, and they're almost they are on the same similar segment, but still the knowledge graph LSTM performs better here, right? So that's kind of a helpful. So there's another question. Uh, are we saying it can handle updating graph database yet? Yes, it can handle updating the graph database. Yes. And another question is, compared with BERT, how better the performance of the graph neural network? Uh, though I do not have any benchmark that I found is available, probably we can test it, how better it can do. Uh, So actually, if we think about neural network, graph neural networks are not different from what we do with BERT or any NLP task, any image processing task. Just that the way we put we actually give the input to the network is different. So it's that you formulate the network based on the input that input data that you have, right? So that's the difference. So we can implement GNN almost everywhere. Okay. So and another thing is the F1 score, which is far better in comparison to the other networks. And in semantics, GCN graph convolution network, they have almost 80% of F1 score. And although the recent trend is having much more better accuracy than this, which you can check with the different data sets like quad it has been compared with, and how better it performed with that. Okay, so that's kind of a motivation of using GNN for NLP, right? So I'll go ahead with that. Now, so data structure as a graph. Right? So just let's understand what is a data structure. Right? So the normal data structure as a graph. So data structure as a graph. So let's understand a basic idea of normal graphs that you have so far. I think almost everyone have an idea of graphs, so how the graphs are formulated, right? So for normal regular data structures, if for images you see there's a sparse matrix, right? That basically, or a adjacency matrix that shows an image, right? In convolutional layer, that we pull the matrix or adjacency matrix from the image uh, pixels, right? So similarly, in time series, we use a structured or regular data structure uh, which has a known kind of a structure already, right? But let's say irregular data structures, where you have something we do not know how they are formulated and how they can change over time, and the how actually they are distributed and linked to each other. So that those things are kind of very unpredictable and changeable. So you see here, like in social network and world wide web, telecom networks, supply chains, biological systems, right? In semantic lexicons, example of in NLP we do these lexicon find formulations. So there also we kind of having a very irregular data structures that gets created. Chemical models, state machines, and call graphs, right? So these are kind of an example of irregular data structures that are formulated around. So there's another question. Is GNN is used only in NLP? Is there a use case in vision and other places? I have explained this already. In short, yes, GNN is used for all the aspects: image, text, uh, is it possible to find the shortest path between two nodes using GNNs? Yes, we can do that. We can find the shortest path. So using GNNs, but always we should be considering that we are using neural network, not for doing small calculations. But however, I mean, if you have a use case where you wanted to find the shortest path based on the GNN, I mean, for all the network and all the nodes in the network, yeah, definitely that could be a helpful thing. I mean, I believe so. There are few examples where where we use uh, that's called. I'll talk about that probably later. So let's say GAT, we have a graph attention network. So where we use attention in finding which path is more having more weightage. So earlier we have, let's say, a node having a connection to node 2,
with a single path, right? So we only know that this can be reached through this path, or the shortest path for that node probably is an another way. But how about giving more weightage to based on the based on based on certain features, or weightage that we get from the network training, right? So these kind of things can be done in GNN.
So a basic structure of GNN is so as I was continuing here, let's understand the basic structure of GNN, right? So it has a node and a edge. So any graph neural network will have any graph data structure will have a edge and a node or vertices. So there are the GNN structure according to the graph. It would be G consisting of a vertices and an edge, and with a set of nodes, right? Node, and which we call as denoted as a V, and a set of edges, right? So nodes are identified by a unique index I consisting, right? So from which are basically from all the nodes, and we call it like an I, or N1, N2, N3, like that, or VI, V2, V3, and that ranges from 1 to mod of V, and it's always a positive number. And the directed edges, right, I to J, is always there present between the uh, between multiple nodes. So there is a direction from let's say node C to node A, and from A to B. So if I have to go from B to A, it's not possible because the directed graphs is showing the direction from A to B. So these are kind of a very basic understanding of a graph data structure. Um, so let's go ahead with that idea. A graph neural network will have a representation like this. Let's say I have a graph data structure like this, or a graph data already I have available, and I am getting initial representation of each node as some with some vectors. So these are basically, you can consider some vector numbers. So these are basically a representation of a graph, and an initial representation of each node, right? So another question is, can we have bidirectional nodes? Yes, we can have bidirectional nodes. Each node will be a vector. Yes, we can have. I mean, we actually have each node weightage as a vector, right? So we can call, we can define or formulate them as a vector, right? So that is an initial representation. So let's say I have that initial representation of the node, and that goes through GNN, right? So my uh, uh, graph neural network. So this is my initial representation of the graph data structure, and that goes to the GNN, the graph neural network, and that gives me a certain number, right? So these probably has been changed for that, the vectors basically changes, right? So once that has been done, then you do a specific task for that purpose, that the business use case, or probably it gives you a binary number for each of these nodes, and it does the feature extraction of each of the nodes based on the and that we get it from the vector from for each node, right? And then we calculate the loss as well for those. So what does initial representation of each node signify? So what does a node positioned at, or probably how a node is connected to the other nodes? What is the um, you know uh,
what exactly a particular node is signifying, what is the weightage. So these things probably can be passed in as a initial representation, right? So a vector, or let's say you, if you consider instead of these uh, nodes, right, I will call it a, let's say I have an image of a cow, and I have an image of a cat, I have an image of some dog, or probably I have some family of dogs here, right? So how these dogs are related to the other animals, right? So these kind of the features that that each of these nodes signifies, right? So those things can be derived or can be called as initial representation. So these, if I already know certain things of the node, right? So let's say I know these are basically from dogs family, or all of them are dogs, and some of the nodes are from these portion are kind of a all domestic animal. So I will call it a semi-structured uh, graph data set, right? So based on what we have, we actually formulate it. So I have another question. How does one build a graph? Is there any method or strategy? We'll look into that. So we have a code for that, how to build a data structure. So it's very simple actually. You denote the nodes and edges for a particular uh, network, and then you decide what would be the uh, I mean, how many nodes and what edges and how much weightage they are considering, right? So I'll just walk through that at the end of this session. So there are once we understand the graph, and let's say I have these initial representation of the graph, and as you see from the previous slide that I have D and E edges, I mean these two nodes are connected to the node F, right? And they have an edges directing to F only, right? So I'm taking D and E here, and that has some kind of vector representation, and that is kind of, I'll say, the current neighbor states, right? So the neighbor is also one of the thing that we in mathematical term we define it as n, right? So here these eta, right? So we call that F has a neighbor D, and E has a neighbor F, and F has a and D has a neighbor F, let's say, right? So these neighbors will have the information collected from the other nodes, right? So let's say here I have D and E, which has some vector representation and the current neighboring states, and those are actually passing a message to the other node. So like D is passing a function which where I'm actually passing the message from D to F and E to F, right? So all these messages are because directed to this, so these are going here, and then you prepare a message from both of these nodes, right? That goes to a filter where we summarize and receive the information from these two nodes, right? The context basically in NLP term, I would say. So these information again pass into some engine where we get the current node state, right? The current node state h and t minus 1, and we get the next node state. So we predict the next node state h and t, right? So any RNN, if you know any RNN network where we actually pass in some value and we predict the next output, right? So yi, right? So let's say if we are passing any input to the network, it gives me the predicted value. So similarly, for timestamp t minus 1, I will be predicting the next node state. right? That's what the neural message passing is. Basically, from multiple nodes we are gathering those information, and those messages are formulated as in one singular vector, or probably you can call it a message for just a high level idea of that. And that goes to engine that could be a these engine. I will replace it later with, let's say, gated GNN or GCN, or probably GAN, right? So there are so many variations of graph neural network. So these can be based on what you are expecting as an output. Okay. So this is the formula that actually defines the states, and the how the I mean, the neural message passing happens between a certain time step with t minus 1, and basically this is nj. So nj is the node states from ni to dot nj types, right? So these will be passed based on um, how many nodes we have, and for each node it will be done the same step. We will be performing the same step, right? So it's basically for each time step we do these message passing from layer to layer in neural network, right? So it goes the state of t0, and then t1, and so on to t4, right? So that's what happens in the message passing, and message goes from the layer 1 to the all through all the layers, right, in a neural network. So then what happens is in TNNs, in synchronous message passing, right? So let's say we have a particular node here, and that passes, I mean, that understands the neighboring nodes, and that passes all the message to its neighboring nodes, right? And then the other node, also the neighboring node also goes for other node, and then the so on. So for all the node, it happens that it passes the messages to all the other neighboring nodes, right? It's not just that particular or single, or is a specific node does it. For all the nodes that we call something, there is something called neighboring nodes, right? So all the neighboring nodes gets the message passed from from their respective neighbors, right? And that kind of helps in understanding where, let's say, there are scenarios where we do not know, uh, let's say there is an I'll give you an example here. So how this helps, so let's say there is a person, uh, Rob, who is a author, right? So based on I mean, he might have a co-author, right? And these are his co-authors. So based on these two data, we can get to know who else has published with R1 or Rob, right? So that kind of information can be predicted, because these neighbor information can be extracted based on what we have from R1 or these particular nodes. So there is a question: a node can get the message from more than one node, message from more than one node, sorry. So yes, it can get so the concept is the neighboring node. So there, a node can have two or four or five neighboring nodes, right? So based on that, it actually gets the messages, right, from the neighboring node and distributes to them. So if I have node here, right, so I can get the information from all of these nodes, right? That's what is neighboring node is. And these node collect the information from its own its neighboring nodes. Okay. Can we call a node as neighboring node even if they are not connected? A node will always be connected at least to one node, right? So there they will have a neighbor. If they are not connected, they are separate graphs. They are different graphs, right? They are not part of the same graph. So in GNN that we get an output. So the output will be H and HT, right? So as in state of those nodes that sorry the GNN layers, right? So that we calculate as a HTN. So if you see here, so XN, right, would be the we apply a sigma with a weight matrix and H and T that we get as an output and a bias, right? So this is what we get, and the binary cross entropy for these would be a yn into log xn, right? Plus one. Normally, this is what we have for any neural network model. So these changes based on what kind of network that we you are using as an engine, right? So that we were showing the gear sign, right? So that based on that it changes the formula. But more or less, there are actually 120 different papers which are showing different types of calculations, or the loss calculation, but more or less the structure of these equations are similar. It's just the same kind of structure. Okay, so GNN in deep learning methods it can be kind of divided into uh, primarily these five categories, but there are so many other categories which is kind of uh, you know uh, coming into the area in GNN area, and they are still in the research phase. But these are kind of popular in terms of the use case and how their how their accuracy and behavior is. So like graph recurrent neural network, GRNN. In GRNN, if you search as a there are another
Recording. Okay, so so as I was saying that there are variations of these deep learning on graphs, right? So there could be GRNN, GCM, or GAM, graph adversarial method. There is something called graph attention network as well. So that is also kind of very useful technique. But we need to see that what which is more suitable for the use cases that we have. Okay, so with that note, I'll go ahead and see the graph type. There is a huge variety of graph types like a directed graph, heterogeneous graph. There could be an age informative graph, dynamic graph. Though I did not explore much on each of these aspects because these are again huge areas, and um, uh, it really needs research uh, uh, to understand. I mean, how much and how much useful or how much helpful these are based on our data set that we have, right? So we'll discuss the popular ones mostly and how they are kind of formulated in recent times. Okay, so with a directed graph, we had DGP, heterogeneous graph with a graph inception, right? So age informative graph, just to touch upon that, or probably just have an idea of this term, and these are like graph types, and with that we have different graph training methods, right? So neighborhood sampling. This is one of the training methods where in neighborhood sampling we have graph stage, which you might have seen, or if you search with graph neural network, graph sage is one of the popular algorithms that has been developed in recent times, and which is doing good with this neighborhood sampling method, and we have pin sage, one of the other techniques, and in that we have fast GCN and adaptive, and then we have SSE, right? So these are basically different variations or techniques of doing the neighborhood sampling, right? Again, then we go for receptive field control. There we have control variate, data augmentation. We have co-training and self-training, and unsupervised training methods. We have GAE, BJE, and ARGA and GCMT. Okay, so these are kind of each of these are different papers. If you search with the name, you can always read about these papers to have more idea. I have noted all of these reference, I mean all of these papers in the reference section at the end of this slide. So graph propagation steps. So in propagation steps, we have convolutional aggregator, we have attention aggregator, we have get updater, skip connection, and hierarchical graph. So in convolutional aggregator, we have again graph convolutional network, which is the popular one, GCN we call. And then in GCN again, we have spectral and spatial, right? So we have a spatial data in spectral again. We divide them spectral network and AGCN, or ChebNet and GGP and GCN, right? So these are kind of an algorithm and the models or neural network model that is being used. And if you have a special category in that, you have neural FPs, Patchysan, and then SSENN, right? So these are, and again this graph stage is a comes into picture of these attention aggregation, right? So you can probably have a look at the GAN, graph attention network. So although covering all of these neural network types in one session is not in scope, but I would recommend to go and check all of these, at least GAN and GCN, and how they are actually working in each of these scenarios and the different data sets that's available. Then we have get updater like GRU and LSTM. We have graph LSTM, and we have gated graph neural network, so GGNN. So we'll talk about these GGNN here. It's more of gated graph neural network. So as a special case for this session, but we just to have an idea of that there are so many variations of these graph neural network, and how they are actually different based on based on the use case, and based on the type of propagation that we chose, right? So here the graph updater is again having these LSTM. With LSTM we have graph LSTM, and graph LSTM can be again divided with a tree, graph, and text, right? In tree we have tree LSTM, graph LSTM, and sentence LSTM. And skip convolution, we have jump knowledge network. These are basically knowledge graphs that are being formulated using these types. And then hierarchical graph, we have ECC and deep pool. Okay, so let's understand graph neural network with gated formulation. So with gated graph neural network, how they are actually formulated. So there is a question: can you give an example where graph database is must or most preferred method of storing information? So there are so many actually. So examples where graph database is kind of very useful. Graph database in terms of how the data is stored, right? So nowadays, I mean, if you have heard about Neo4j, is one of the very popular databases, graph databases. There, they actually store information in graph structure, right? So those are stored in the graph DB, right? So
though I will say neural network um, uh, actually extracts the information from graph database, right? From graph I mean extracts the information from uh, graph based data set. It could be structured or semi structured or unstructured. It could be completely unstructured data. So let's say somewhere where you do not um, you don't know that how the data set is formulated, you always can use ggns. So as I gave example at the beginning of these slides, right? So if you see here, um, social networks, uh, world wide web, these are kind of a very important aspects, right? And where we do not really know that how the data is formulated. Telecom networks or supply chains and biological systems where chemical formations of the molecules, right? So that kind of changes based on reactions or based on the molecule uh, interactions, right? So those kind of things are kind of tracked based using graph neural network. So there's an interesting question that there is a graph neural language like Cipher to get the information directly from Neo4j. Then why is GNN required? So again, the question comes with training the neural network, right? So with let's say when we talk about CNNs, right? So we get the information from a particular image, and based on that we predict what would be the next image, or probably when we do image segmentation, we find the difference between the images, right? So similarly in graph, probably in Neo4j, I'm not aware of Cipher how intelligent information it can get. It, like if you compare with a structured database, we can have a query and we get some information, but we do not get a contextual information from a database. So I will use LSTM here instead of I would not call it just GNN, just not a graph neural network. I will use a LSTM tree-based graph structure where I can have a context from the previous state, right? So I can have more information or understanding of what's happening with the previous node, or what exactly I'm getting from the previous node. So I can predict what would be my what would be the output from the next node. So I don't think the normal or conventional data sets, or probably a graph databases like Neo4j would be able to, I mean, will have a prediction mechanism where it can predict that what would be the next neighboring node is consisting of. All right, so those kind of challenging problems cannot be solved normally or without using graph neural network or neural networks in specific, I would say. So any neural network we use for different purpose. So mostly it's an contextual and computational uh, aspect of a large number of data that we get, right? I hope that answers the query. So with that, I will go ahead with the next slide. So GGNs are GGNs are unrolled recurrence for a fixed number of steps and just use back propagation through time with modern optimization methods. Also changed the propagation model a bit to use gating mechanism like a LSTM and GRU. So LSTM and GRU also can be used or changed as a gating mechanism. So in gated neural network, it is up to us that how we are going to we are going to formulate the model or change the model or structure the model. So benefits of GTNS. So no restriction on propagation model, does not need to be contract and map.
it will have initialization. I mean, there one more thing that initialization matters now. So problem specific information can be fed in as the input. Another thing is learning to compute representation within a fixed budget, and it has a getting makes the getting mechanism, right? That makes the propagation model better. So let's say we have an initialization of GGN like this when problem specific node is annotated with HV. So if you see here, the information goes from red to green node, let's say A to B, right? So the reachability problem, can we go from A to B? So it is easy to learn a propagation model that copies and adds the first bit to the node's neighbor, right? So it is easy to learn an output model that outputs yes if it sees the red and green pattern, or otherwise no. So here the output is yes. But what if we have something like this? So where the path is, so here if we ask the question that can we go from A to B, right? So here A to B means the red to green. So here it is not possible. Output is no, right? So sorry, this is corrected. It is no. Okay. So problem specific node annotation, in practice we paired node annotations with extra zeros to add capacity to H, right? So we do that for node annotations, but normally any propagation model or GNN propagation model with getting or the other minor differences, you'll have an unrolled step like this. So you see here, it goes to H, I mean, it goes with HT minus one steps, right? So H, H1, H2, H3, and H4. So all of these are having T minus one step, and then that connects to these, the neighboring or unrolling step to the other node, right? So as you see here, h1 t minus 1 to h2 t, and h2 to t minus 1 to h4 t, something like that. So here the directions are kind of from both 2 to 1 and 1 to 2, apart from what we already have as a directed graph, right? So these are the unrolled steps that we get from a particular graph, or we can derive from a particular graph. Okay, so in gated GNNs, what we do is the same structure where we get the current neighbor states, and then we pass in as a message, and then prepare the message and summarize the received information, and then we get the current node state and the next node state, right? So only thing is here in HNT we use the GRU, right? And GRU will have these HNT minus one or M steps, right? So this is what it actually changes. And if you see here ek, right, so that basically for each node what feature and what exactly is different from the other node or changes as an information. So that's what is notifying. So we get a sum of all of them, which is basically derived as an M here in the GRU network, right? So graph notation of an adjacency matrix. So we get, let's say, 0, 1, 2, they are connected to each other like this, as an ABC, right? So we get an adjacency matrix like this, and then we get a node, right? So ABC. So we actually do a dot product of them, and then we get these particular matrix, right? So so how so the total matrix calculation is actually in stepwise is formulated like this: the node state, and then the message to be sent, and received messages, and then we concatenate as an update, right? So at the node state we get the states of all of these nodes with ht, n0, and n1, and nk. So the number of nodes into d, right? So and then messages to be sent is mkt, which is ek into ht of number of nodes. So we get the node state multiplied with the ek, that is the age of each of the nodes, right? So and then we get the we receive the messages with the rt, which we actually sum of all of them, and the adjacency matrix, which is a into mkt, right? So these rt is again
passed as an update, and which we call as the HT plus 1, where is GRU gets the HT and the RT, right? So the HT here, the node states, and we pass the received message, the RT, right? So if we use a vanilla RNN here, then we probably will use a sigmoid function, and with that we'll do an addition of the UHT and weight multiplied with the RT. Okay. So A is the adjacency matrix. There is a question, what is A? So A is the adjacency matrix that we get from any graph, right? So that I was showing in the previous slide, that an adjacency matrix looks like this, right? So to get for any graph, we can get an adjacency matrix like this. Okay. And EK is the another question is, what is EK? EK is the age for each, let's say, for each node we have an age connected, right? So all those information from each of the nodes we denote it as an EK, right? So if you see here, let's say this is an age, this is an age, E1, E2, whatever EK. Okay. So in GNN, right? So as a sample code, if you see here, I just took it from Spectral. There is a library for Python which is very easy to understand, where we get the step of the node, and we pass in the input as a sparse as true. So you can, if you do not have a sparse matrix, you can say that sparse is false. So that goes as an adjacency matrix and the input of the node. So then you formulate the graph convolutional, I mean GCN basically. So with the ReLU function on top of that, and then probably you actually define the dropout for each of these nodes, and then x2 is the total in class on combination of x1 and a1, right? And then you define the model, and model will have an input of x in and a underscore in, right? And you get an output as an x2. So x2 is this is the output that we get. Okay, just to have a quick idea of what GNN is formulated. So the applications of GNN is in physics. We can apply in molecule. In images, we can apply the GNN. We can have a text in dependency parsing. We can have GNN. I mean, we can use actually GNN. And in social network, also we can use graph neural network. And in generation, graph network generation or graph generation, we can use GNN. Okay. So there is a question, what is F and what is doing in the code. So I will come to that. I will have the code demo so that I can quickly discuss about that. So almost end of the slide. So application of the graph neural network, as we see here, the in this left side you see the applications. So I mostly taken all of these are NLP applications like neural machine translation, relation extraction, text classification, sequence labeling, sentiment classification, and sentiment role labeling. So let's say neural machine translation that can be used with the GGNN, gated graph neural network, right? And for relation extraction, we can use GCN, graph convolutional network, or we can use text GCN, or we can use tree LSTM, right? And for text classification, we have a lot of options like GCN, GAT, DGCN, and text GCN, and sentence LSTM. Right, for sentence classification, we use tree LSTM, and for semantic role labeling, we use syntactic GCN. So there are a lot of applications and algorithms that can be used based on the use cases that we have, and the deep learning models are again different for each of these use cases or the algorithms that we are using. Okay, so these are the references for understanding the graph neural network. You can probably have a look. Okay, so we'll almost done with the PPTs. We'll go ahead with a quick, code walkthrough. So, so I used a library called Spectral here, and it's a neural graph neural network based library. So that kind of, it's a Keras based library and uses an internal graph mm, network. So in this example, the simple graph convolutional network, right, in GCN, for semi-supervised classification of nodes being used. And this is a simple but challenging task that consists of classifying text documents in citation network. So in this type of graph, each node represents a document, right, and is associated to a binary bag of words attribute. So see, if you understand these examples, it's a very uh, kind of complex example in terms of if you think to do with any other method. So where one, if a given word appears in the text, zero otherwise. So we actually denote that as in one or zero. If the document cites another, then there exists an undirected edge between the two corresponding nodes. So finally, each node has a class level that we want to predict. So this is a transductive learning setting where we observe all of the nodes and edges as a training time, but only a fraction of the level. And the goal is to learn to predict the missing level. This is what the goal of the task. So the dataset is citation module of spectral. I mean, basically, it's having dataset dot citation module from spectral that lets you download and load three popular citation datasets, Quora and SiteShare and then PubMed. Right. So in one line of code, you can use that. So let's say here I used from spectral.dataset import citation and AXY train mask and validation mask. We have the citation load data, Quora, and then we got the shape of all of them. So if you see the steps of all of these data sets as a N and F, right, which is the A shape and an X dot shape here, and then we get the classes of them, right? So we get as 227, I mean 2K almost as a and 2K by 2K matrix, right? So these will load the network adjacency matrix A as a SciPy sparse matrix of step n dot n, right, n comma n, and node feature x of step n comma f, and the labels y of step n comma n classes. So this is what I think that answers the question what is f here, and the loader will also return some boolean marks to know which nodes belong to training, validation, and test, right? That's what it is. Uh, so what is x? So if you see here, right, I explained what is x here. So the node features x of shape n comma f, right? So that is the x here. The loader will also return some boolean mask to know which nodes belong to training, validation, and test set. So now we'll create the GNN, right? So the GNN creation will be from here, the building the model. So no, I mean, this is basically no different from the Keras model, but we'll need to provide multiple input X and A uh, to the graph convolutional layer. So we have these, as I explained in the PPT. So X in as an input of shape f comma, right, and A as an adjacency matrix for node where we have a sparse as true, and then we get the x1 and x2, and then we pass in that to the model and we get the output as an x. Okay, so we got the GNN or module built. That spectral actually this library helps to build these very easily. We if you see the spectral
library, we have defined how they should be formulated, how they should be created. Okay. So note how we used the familiar API here, right, to create a GCN layer and as well as the standard dropout layer to regularize our model. All feature of Keras are also supported by Spectral. One thing that to note down. And also as the elements of our dataset are the node themselves, we are telling Keras to consider each node as a separate sample so that the batch access is implicitly defined as none. That's why we have blank here. So there are many libraries which we can use for graph neural network. Though I haven't discovered much about the libraries with GNN, but Spectral is one of the thing that I come across and which is good with the latest Python version and Colab. I mean TensorFlow and Keras version. But we can always explore with PyTorch. We do not. I do not see very latest models with latest PyTorch version because it earlier it used to have a torch graph. So currently, I'm not sure if that has been updated much with the PyTorch module. So that with the training the GNN, right? So when training GCN, we have a pre-process the adjacency matrix to add self loops, and we scale the weights of nodes connection according to its degree. And then some layers in Spectral require a different type of pre-processing in order to work correctly, so that we need to decide what layer that we are formulating. So in this example, pre-processing required by GCN is kind of, you know, we kind of use this line of code, and that's all. So what left now is the compile and train our model. So this compilation happens model.compile, and then you provide the optimizer and the loss and the weighted matrix. Okay, so this is what we get, and then we use the weighted matrix argument instead of usual matrix here. This is due to particular semi-supervised. This is to be noted here, that semi-supervised problem. That's why we are dealing with these with the weighted matrix, and has to do with the Boolean mask that we loaded earlier. So we use the Boolean mask here. So then we do the preparation of data and then we train the model. Okay. So few things to note here. We have a set batch size as n, and we have a shuffle as false, and uh, this is because the default behavior of Keras is to split data right into batches. You already know, and the shuffling of the adjacency matrix along one axis and not the other means that that row I will represent a different node than the column I. Right, so that's the reason we do that. So what are self loops? So self loops are like a recurrent thing. You can call them, right? So that's why we are calling them as a self loop. And the only solution is to take all the node features at the same time, hence batch size is n here. And finally, we use the train mask and validation mask. And the only thing that changes is the mask here. So this is also we use weighted matrix. That's the reason that we use weighted matrix. Okay. So that's the thing that we get the test accuracy and the test log. Okay. This is a simple and very simple example, but I would recommend to try with different libraries and how GNN actually works. In Kaggle, we have a lot of competitions with the Gated neural network and GCN basically. For MNIST dataset, we have certain competition and notebooks. You can always try out those and how you can see how GNN behaves. Okay. So that's all from my side.